Okay, great. So I will be talking about relativistic spin hydrodynamics. So I will start with ideal, and then I will also move on to including dissipation in relativistic spin hydrodynamics. Okay, so let me quickly give some motivation of why I am doing what I am doing. So basically, it's motivated by application to relativistic heavy ion collision. So you see, this beautiful picture is made by Chun Shen. So I will just use it and acknowledge him. So basically, in this collision of two nuclei, so hydro plays a major role. We know this, that one can use this the hydro models to explain a major part of the evolution of QCD matter, which is formed in collision of two nuclei. So much effort is, of course, being put in understanding the pre-equilibrium dynamics. Okay. However, once the system is close to equilibrium, we can straight away switch on hydro and explain and basically evolve till kinetic freeze out, till the point where all elastic scattering also ceases and the momenta of the particles are fixed, and which then free stream to the detector. Okay, so this time scale is roughly 1 Fermi to 10 Fermi over C, and that's the major part of the evolution. Okay, so hydro plays a big role in understanding heavy ion collisions. So how does hydro work? So initially the motivation was that that since the QCD matter, which is formed in heavy ion collision, so hydro would be applied to take the initial state spatial information and convert it to final state momentum anisotropy. Okay, so this is on the left hand side. This figure here I show that the overlap zone, which is at the initial time epsilon, has this eccentricity, which is a spatial anisotropic, and once we apply hydro, then we see that the momentum anisotropy of the observed particles. So the one which corresponds to this elliptic eccentricity is the elliptic flow V2, and one gets so this anisotropy is observed in the experimental measurements. On the right hand side, this is one of the earliest plots by Paul. So here it's demonstrated that if I plot V2 as a function of PT, then one needs viscosity to bring down this over prediction of V2 from ideal hydrodynamics. So viscosity is needed to degrade this conversion efficiency of initial state eccentricity to final state anisotropy of momenta, and that is required to explain the data. Good. So this was the earliest motivations of using hydro to heavy ion collisions. And the hydro equations that we use. So basically in this table, I compare ideal versus dissipative hydro. So ideal hydro equations are closed along with the equation of state, 6 unknowns. So this equation for the dissipative part is written in Landau frame. So which means that the dissipative corrections to T mu nu is orthogonal to U mu. Okay. So here you see that the quantities in red are the dissipative corrections or the dissipative part of the energy moment tensor, and the capital pi is bulk viscous pressure, pi mu nu is shear stress tensor, and n mu is the dissipation to conserved current. Okay, so one needs additional equations for these dissipative quantities apart from the conservation equations, which is conservation of energy momentum tensor and conservation of current. Okay, so this quantity delta mu nu has been introduced, which is a projection orthogonal to U mu. So we will be using this. So I just write it down at the beginning. Okay, so more or less this is a picture of hydrodynamics, ideal versus dissipative hydro. But of course, one has to obtain equations for capital pi mu nu, and n mu, and then we can put it in the model. So the simplest equation that one obtains is the Navier-Stokes, and the Navier-Stokes is very easy to feed. So the intuition for the Navier-Stokes is very easy. So in terms of, so in very simple terms, shear basically tells you fluid's resistance to shearing forces. So basically, if I apply a force along x direction and look at the velocity gradient along y, then that's what my shear viscosity or shear stress tensor tells me. Similarly, bulk viscosity tells me about the fluid's resistance to compression. Okay, and of course, the charge or heat conductivity, it's fluid's resistance to flow of charge or heat. Okay, so this is the basic idea of dissipation. Of course, one has to extend this notion of dissipation because the relativistic Navier-Stokes theory lands up in problems of causality and instability, and therefore one has to go beyond the Navier-Stokes regime. And once you do that, you enter into an era of rich physics where basically you encounter phenomena like attractors, and so this is something which is for some other time, and this has been actually discussed in great details in this workshop. What I will so let me quickly just highlight the success of hydro models in heavy ion collision. So this is one of the state-of-the-art calculations, basically the music calculation. So you see that hydro has been able to explain almost all observables, all soft observables in heavy ion collision. Okay, it seems to work too well. So it seems to work so much beyond expectation that it has become a matter of concern, and the community is trying to understand what is really happening in beyond this validity of hydro beyond its regime of applicability. Anyway, so what we will focus on is another aspect of in relativistic heavy ion collision, and that is generation of angular momentum. So angular momentum is deposited by the colliding nuclei. So a very fast moving nucleus, when it collides, the fact that it's not homogeneous that in density, and so the nucleus has a density distribution, and the fact that some amount is left over and there is a momentum change. So therefore, what is left in the center, in the overlap zone, has angular momentum, a large amount of angular momentum. A rough estimate tells us that it's of the order of 10 to the power 5 h bar, which is quite huge. So much so that it actually can show up in the measurement of polarization of observed particles. So this was recently done. I will, in the following, I will show a few slides taken from Beccatini's presentations, and I will just to motivate what one gets from measurements of star collaboration. So global lambda hyperon polarization was measured, and recently, as shown in this figure, K star has also been measured. Both are different, lambda being baryon, whereas K star being a meson. However, still the point is that the polarization has a non-zero polarization, which is a telltale sign of angular momentum, which we will see later why I claim this, and that has been observed, and this has and it was actually featured on the cover page of the journal Nature. So it actually tells you that there is this very intense swirls. So subatomic swirls is what they are called, and the first evidence of quantum effect in relativistic hydrodynamics. So hydrodynamics, the way we formulate it, is mostly classical treatment. So spin polarization observables spin is supposed to work in the quantum phenomena. It's a quantum phenomena. So it seems like this first evidence of quantum effect in relativistic hydrodynamics. So the plot shows polarization as a measure in percent versus the colliding energy of nuclei. Okay, so you see that the polarization of lambda in this case that has been plotted is of the order of few percent. So mostly of the order of few percent. And we will see that a very rough calculation immediately leads to this order of magnitude. So how do we do this? So we can look at polarization by rotation. So one can take an ideal gas in a rigidly rotating vessel. So the vessel is rigidly rotating. However, the gas is not rigid in the sense that there is a profile to the rotation. So now at thermodynamic equilibrium, the gas will also have a velocity field. So that is, so if there is a global equilibrium is achieved, then the gas will have a global vorticity, so that it will have a velocity field. So V due to rotation can be obtained by P equal to omega cross X. Okay. Now for a co-moving observer, so the one who is rotating with the gas, then one has simply, so the distribution function is basically given by the kinetic energy due to the motion of the particle and due to the velocity of the rotation. Okay. Now one can easily, so one can do this calculation and go to the external inertial observer. So in the frame of inertial observer, what we see is that the kinetic energy term P square by 2m is there. However, there is a omega dot L being the angular momentum. So omega dot L kind of term appears for the distribution function. So it is so basically one can, it's quite natural to extend this notion of so L being the orbital angular momentum. It's quite natural to extend this to include spin as well. Okay. So the L plus S being the total. If there is intrinsic spin to the particle, then L plus S becomes the total J. Okay. So a rough calculation about polarization, you immediately see that the polarization, the amount of polarization is proportional to omega over T. So for gas at room temperature or STP, let's say, with very large rotation, omega at 1000 hertz, even then you see the polarization is quite small. So because of the fact that there is a H bar sitting in the numerator. Okay. However, for relativistic nuclear collision, one immediately sees that the order of magnitude is few percent. So this order of magnitude is calculated in a very simple way. So we assume that the edges of the rotation, so globally rotating fireball, the edges is almost at the velocity c. So basically R omega, where R we take freeze out 12 Fermi. So then R omega is equal to c, and we put this number here, take the temperature to be 200 MeV, and you get this few percent which was observed experimentally, the polarization. So basically the rough order of magnitude calculation tells you that few percent of polarization can immediately be calculated. Okay, of course, one has to go into details of, so if one wants to apply hydro, then one has to go into more details of doing this calculation. However, this thing is not new. So this fact that one can obtain polarization by rotating fluid is not new. So this dates back to 1915 Barnett effect, where Barnett showed that one can obtain spontaneous magnetization. So this magnetic polarization one can obtain of an uncharged body by simply rotating the uncharged object at large velocities. Okay. And this magnetization was also found to be proportional to omega. Okay. So the way it works is, however, this is a dissipative aspect in the sense that that the orbital angular momentum is transformed into the spin. Okay, so dissipative transformation of orbital angular momentum into its spin constituents, and then the angular velocity decreases, which leads to appearance of a small magnetic field. However, it also leads to a heating of the sample. Okay, and this phenomenon requires a spin orbit coupling. Okay, and the converse of this Barnett effect was the Einstein-De Haas effect, the only non-Gedanken experiment of Einstein, which tells you that if one puts a ferromagnet in magnetic field, then it rotates. Okay, So rotation of ferromagnet originally at rest, if one puts it in the external magnetic field. So the external magnetic field aligns the spins, and since there is a spin alignment, then what happens is that because of the spin alignment and the fact that the object, the ferromagnet, was originally at rest, to conserve angular momentum, the magnet will spin in the opposite direction. So that's the Einstein-De Haas effect. Okay, this is also an irreversible process, which is also accompanied by heating of the ferromagnet. Okay, so far the motivation of why one should look into angular momentum conservation in heavy ion collision explicitly. So we will also see in more details what it actually means, why it is not automatically conserved by the conservation of energy momentum tensor. So we want to apply relativistic hydrodynamics to understand particle polarization. So, and hydrodynamic evolution should ensure that total global angular momentum is conserved. Okay, and this formulation would therefore require that total angular momentum conservation should be necessarily fulfilled, and the polarization, and also to have polarization, the process is dissipative in nature, so ideal would not work. So ideal spin or angular momentum conservation in ideal hydro would not be enough. So one also needs dissipation to be included in the formulation. So that's what we will do. We will discuss the formulation of ideal and dissipative hydrodynamics with angular momentum conservation. And the framework that we would use is kinetic theory, relativistic kinetic theory. Okay, so before we go into angular momentum of fluids, let's first quickly go through the orbital angular momentum of particle and angular momentum conservation of particles. So L is x cross p, we know this. So this basically one can look into the components of the angular momentum L in terms of the Christoph, the Lebesgue symbol epsilon ijk, and then one can form the dual of that. Okay, so you know that both these descriptions in terms of vector L and the tensor Lij are equivalent because the number of degrees of freedom in Li and Lij are the same, keeping in mind that Lij is an antisymmetric tensor. Okay, so then Lij is just this xipj minus xjpi. Okay, so in absence of external torque, we know that angular momentum dl by dt is 0. It's conserved. Okay, and we also have del I of Lij equal to 0. Simply from this form, we see that del I of Lij is 0. Okay, this treatment is valid for non-relativistic point particles. Okay, so how do we generalize to fluid momenta? So we have to use, so instead of the particle momenta, so the momenta of the point particle, in this definition, we need to use generalized fluid momenta. So the only generalized fluid momenta that we know is the energy momentum tensor. So this is how one can obtain the orbital angular momentum for relativistic fluids. This is how it is defined. So we immediately see that from the previous definition of angular momentum Lij for point particle, which was a 2-rank tensor. For fluids, it becomes a 3-rank tensor. And keeping in mind that the energy momentum tensor is conserved, we see that d lambda of L lambda mu nu is just the antisymmetric part of T mu nu. But classically, T mu nu is symmetric. Okay, so d lambda L lambda mu nu is conserved. So this orbital angular momentum is conserved. Okay, automatically conserved if T mu nu is symmetric. So this is very nice. So if T mu nu is symmetric and there is only orbital angular momentum due to a global motion of the part, so due to the motion of the particles, then we need not worry about conserving angular momentum, total angular momentum separately. However, when the medium constituents have intrinsic spin, then the total angular momentum has also the spin and couplings. Okay, so the orbital part, the spin part, and the couplings between the orbital and spin. Therefore, now one has to worry about the total angular momentum. It's not just the orbital part anymore. But still there is some simplification, because suppose if I ignore the couplings as a first calculation, if I ignore the couplings and just take the spin, then in absence of coupling terms, and because I am dealing with classical T mu nu, then the spin seems to be conserved. Okay, and this is what we call spin hydrodynamics. So now we'll go into some technicalities. So how do we start constructing spin hydro within kinetic theory? So first we introduce the spin 4 vector, such that in the particle rest frame, the spin for 4 vectors, the rest frame quantity is denoted by star. So it is in the particle rest frame, the spin 4 vector is space-like. So it is space-like in general, but in the particle rest frame, the time-like component is 0. So it is orthogonal to the particle momenta, because in the particle rest frame, the particle momenta is just mass and the other components are 0. And the length of the spin vector, that which basically one can calculate minus s square, which is minus s alpha, would be just j into, so s into s plus 1. So this is this s square, half into half plus 1. Okay, so that is the length of the spin vector, which we know from quantum mechanics. Now we start with spin half massive particles and introduce their internal angular momenta. So internal angular momenta, s alpha beta, we can construct by using the spin vector, this spin 4 vector, and the particle momenta. Okay. So once we have constructed this, we can of course construct the dual of this, and we see so the dual, and we know the normalization of this S alpha. Okay. So the equilibrium distribution function, if you remember, in the example of rigidly rotating gas, so the equilibrium distribution function now becomes a function of S. It's a function of X, the position, the momentum, and now it also becomes a function of S. Okay. And the S part is given by this term omega mu nu, S mu nu, and the equilibrium XP is our usual Jetner form, this Maxwell-Jetner form. So beta mu is this temperature, so basically U mu by T, and this psi is the ratio of chemical potential over temperature. Okay, for particles and antiparticles, we have plus and minus signs. Okay, and this omega mu nu, which we call the vorticity tensor, this is the quantity which is basically like the Lagrange multiplier for spin. So we had, so similar to the fact that beta mu is a multiplier for momentum, and this psi is a multiplier for the number, the current. Similarly, we have omega mu nu, which corresponds to the spin. Okay. So now, so once we have this distribution, this equilibrium distribution function, we can start constructing the hydrodynamic quantities by doing suitable, by integrating over the particle degrees of freedom. So the particle degrees of freedom that we have are the spin and momentum. So we introduce the spin integral measure, okay, which this delta function, the first delta function, it constrains the length of the spin vector. So the equation here, that is constrained by the first delta function, and the second delta function ensures that the spin vector is orthogonal to the particle momentum. Okay, and it is suitably the part which you see outside, m by pi s is a normalization which tells us that if I integrate over ds, and it should give me 2, which corresponds to so 2 is the number, 2 degrees of freedom plus half and minus half. Okay, and if I integrate over s weighted with the distribution function, then that should give me just the Maxwell-Jetner form, the Maxwell-Jetner distribution. Okay, so basically, if I integrate over the spin degrees of freedom, then I should get back my kinetic theory, the original kinetic theory without spin. Okay, that's what integral over S does. And we also introduce the momentum integral measure, which is the Lorentz invariant measure for the momentum integral, which is well known. This is d3p by 2 pi whole cube e. And the next, so using these integral measures, the next step is to construct hydrodynamic quantities. So we use the usual definitions of charge current, n mu in equilibrium. So that is, now the integral is both over the spin and the momentum degrees of freedom. But the weight, so it's weight with particle for momenta times the difference of the particle and antiparticle distribution function. This is net charge current, okay, which is conserved. Similarly, one can now what one can do is one can use the form of the distribution function which we introduced and integrate over the degrees of freedom. So integrate over the spin and the momentum degrees of freedom. However, doing this integral turns out to be, in general, it turns out to be a bit problematic. It's, till now, we have not managed to do it in general. But the point is, since we observed polarization, which was quite small, of the order of few percent, so what we can do is we can try to expand this in the linear, in the limit of small polarization, and only deal with linear in omega. So basically, we can do a perturbative treatment. So this exponential one can expand and keep the linear term in omega. And then we can integrate over the spin degrees of freedom, spin as well as the momentum degrees of freedom. So we obtain this n mu, okay, which is, so this conserved net charge current that we obtain turns out that it doesn't get any contribution from this spin in the linear correction, doesn't contribute to net conserved charge current. Okay, we have seen that if we consider the quadratic correction, then the correction would indeed enter, but in the linear regime it doesn't. So similarly, one can construct the energy momentum tensor. So the form remains the same. The only thing we have to keep in mind is that we also integrate over the spin degrees of freedom. Okay, and then of course one can use the same thing, same perturbation treatment, and do an integration in the limit of small polarization. And the energy momentum tensor also turns out that it does not get any contribution from from omega, or basically from spin quantities. Okay, and it is what we would usually get in relativistic kinetic theory. Okay, and the expressions for energy density and pressure can be found by integrating over the S and dP. Okay, so you see that P0 is the one which is, so the zero quantities we denote is the one which does not contain the chemical potential. So basically, it's the distribution function we put chemical potential equal to 0. So that's PC. That's the quantities with subscript 0. The next thing that we define is the spin tensor. So this definition is what we provide. Okay, so this is not used from the previous known definition. So we adopt this following intuitive definition for spin tensor. Why it is intuitive? Because what we do is we weigh it with the spin tensor and consider the flow of that. So basically, this is the spin flow tensor, right? So this is spin tensor, and weighing with p lambda means that we are looking at and integrating over dp and ds means that we are looking at the flow of S. Okay, so this is what we define intuitively. And then again, one can, in the linear or small polarization limit, one can do the integral and one obtains this expression. This expression is what I show here is the one we obtain for ideal spin tensor. So here the square brackets on indices means anti-symmetrization of those indices. Okay, and then there are the coefficients which are given here. Okay. Right. Now, how do we know that this intuitive definition of S lambda mu nu is indeed correct? So what one can do is one can define the entropy 4 current. So entropy 4 current, we just adopt the Boltzmann definition. So this is what you have from the Boltzmann definition. The only thing is that we of course integrate over the spin degrees of freedom as well. And then using the previous definition, but here in this calculation, we do not do a perturbative treatment. We treat it in the general case. Okay, so we do not consider small polarization. So all we need to do is we consider the previous definitions. Then the entropy current can be written in the form here. Okay, and then using the conservation laws in equilibrium, we see that the entropy for current is indeed conserved. Okay, so it turns out, and of course that involves the contribution from spin to the entropy for current and the conservation of spin current. Okay, so everything turns out quite neatly that it must be consistent. The definition that we had here for S lambda mu nu must be consistent. And this is exact and up to all orders in omega. And this provides support for the form that we assumed for S lambda mu nu. Okay. So ideal spin hydrodynamics, we have the conservation of these three quantities. So conserve net charge current, the energy momentum tensor, and the spin tensor. Okay. And we see that the entropy production, the contribution to the entropy production from spin polarization tensor also enter at quadratic order, and therefore on the entropy production from so no effect on entropy production at linear order. Okay. So what it means is that for the standard hydro equations, so conservation of energy momentum tensor and net current are not affected by polarization at linear order, and therefore at linear order, so one has the hydro background, which is the usual hydro, so that evolves independent of how spin evolves, and spin, however, spin depends on the evolution of this hydro background. So the spin polarization evolves on top of a hydro background, which is not affected by the spin evolution. Okay. So next, we will try to include dissipation. So how do we do this? How do we include dissipation? So since we are dealing with distribution function, we would like to have an evolution equation for the distribution function, which is something like a Boltzmann equation. So what one can do is one can show that using Wigner function and its Clifford algebra decomposition, the distribution function f, which is a function of x, p, and s, indeed follows a Vlasov-like equation. So in absence of collisions and mean field, one can show that this distribution function follows a Vlasov-like equation. So one can write down a Boltzmann equation with some collision term. Okay, and for the time being, we ignore any mean field. So for example, we do not consider any magnetic field for the time being. We just see the effect of collisions on the evolution of the distribution function, which depends on position, momentum, and spin as well. And for simplicity, let's start with relaxation time approximation for the collision term. So given this relaxation time approximation for the collision term, we can put it here, this RTA, and solve for delta F. So the first in gradient expansion, the first order correction to the distribution function in gradients can be calculated here. So this is the form of delta F. So we will use it to obtain dissipative equations. Before that, let's consider the dissipative corrections to the conserved quantity. So now n mu should be n mu equilibrium plus some delta n mu. So we will have corrections to the equilibrium distribution function, to the equilibrium conserved net charge current, to the equilibrium energy momentum tensor, and the equilibrium spin current, spin tensor. Okay, so those are represented by this delta n mu, delta t mu nu, and delta s lambda mu nu. Okay. Now, in RTA, where the collision kernel is given in this simple form, one can take suitable moments of the Boltzmann equation, and so the suitable moments of the Boltzmann equation. So moments mean that we weigh with certain quantities and then integrate over ds and dp. So what we see is that the zeroth moment leads to the conservation of n mu, zeroth moment in momenta. The first moment in momenta integrated over the momenta and the spin leads to conservation So basically del mu T mu nu. So it should be conserved. So provided the criteria below are fulfilled. Similarly for the spin current, the spin tensor. Okay. So the conservation equation provides the matching or frame condition. Okay. So you see the first two conditions are well known. These are the Landau frame conditions. The last one is like an extended Landau frame. Okay. So all dissipative currents are orthogonal to fluid 4 velocity. And this is the fact that RTA works only in Landau frame was well known. Also for spin, it turns out that we have to use the Landau frame, an extended version of that. So now we can express the dissipative corrections to net conserved current T mu nu and S lambda, and as well as spin tensor in terms of delta F. Okay, and remember that we had the first order solution from the Boltzmann equation where the delta F we obtained. So all we need to do, and this is the calculation that we did in the linear regime, linear in omega. So we need to take this delta F, put it in these integrals, and integrate over S and P. And this, since this is the first order, so this is first order correction to the distribution function. So we would expect to obtain a relativistic counterpart of Navier-Stokes equation for spin hydrodynamics. So what we get here, so delta N mu is the usual form. We do not have any up to linear order in omega. We do not have any correction in terms of gradient of omega. Okay. Similarly to delta T mu nu as well, we get shear stress tensor and bulk viscous pressure, the previously known forms, and we do not get any new contribution. However, the new thing that we find is the dissipative correction to spin tensor. So this has corrections coming from this scalar expansion term, a derivative, so space-like derivative of the chemical potential over temperature, psi, or the shear, so this shear tensor, sigma, and the completely new term, which is basically a first order derivative of the polarization omega. Okay. The transport coefficient beta n, beta pi, and beta capital pi, these are found to be, so they remain the same. They do not change from what we usually obtain. Usually it means in absence of spin conservation. However, these coefficients, there's a transport coefficient for spin, have complicated forms, and they are listed in this paper, which I have provided the information below. So the transport coefficient corresponding to spin dissipation can be obtained. What still remains to be understood or to be done is the proper decomposition of this. So decomposition in the sense that delta T mu nu could be decomposed as shear stress tensor and bulk viscous pressure, and then we can try to apply intuition to how the dissipation works. So this is still a step which we need to do. We need to find proper decomposition for this dissipative correction to spin tensor, and then we need to find how the dissipation works. However, the mathematical form is obtained here for the first time. So there are other parallel approaches from Wigner function formalism pursued by the Frankfurt group, and then there are approaches based on Lagrangian method, which Giorgio has been working on. And regarding all these formalism, a very useful review on spin hydro can be found in this review article by Wojtek and company. So basically, I have not gone into the details of how everything in this spin hydro is derived. But however, what I wanted to impress upon is that this is a relatively unexplored area of research, and much work is needed in this direction. And so after the formulation is done, one needs to apply the resultant hydrodynamic model to understand this polarization observables in heavy ion collision, and all this is really unexplored. And I mean, there are several groups working on in this direction. Right. So thank you. I probably finished before time, but we have more time for discussion.
Thanks, Amaresh. Actually, you have finished before time. It was a very nice pedagogical talk and very interesting too. So just before taking questions, I just want to point out that we asked the speaker, including yourself, to email the slides at this address, program@icts.res.in, the same address from where you get your Zoom links, so that we can upload them soon. Okay, now we should take questions. So Ashutosh has a question already. Okay, maybe you can ask yourself, Ashutosh.
Hi.
Hello.
So my question is, what are the constitutive relation for the spin parts?
Yes.
Like you had for the pi and.
Right. So that's what I was trying. So this is this delta S lambda mu nu, right? So
Right.
The next step. So this is the total correction, non-equilibrium correction to spin tensor. Okay, delta S lambda mu nu. So like delta T mu nu, which you could split into shear and bulk viscous bulk part, right? So then you can obtain constitutive relations for pi mu nu and capital pi and so on. We also need to first decompose this. So probably that is the constitutive relation that you mean.
At first, like pi mu is related to sigma mu in that. In
right.
That sense.
So in that sense, this is the general constitutive relation where you see delta S lambda mu nu is related to theta sigma derivative of psi, and derivative of omega. Okay. So essentially what it means is that delta T mu nu, we can also relate it to, well, so the point, so you're absolutely right. Still some work needs to be done in that direction to understand the constitutive relation in terms of sigma, so like pi mu nu and capital pi, that decomposition still needs to be done.
Yeah. Right.
Okay, there are other questions too. So Sayantan is asking, what are the dominant dissipative processes for the spin?
So the beauty about RTA is that, well, all the dissipative processes that could appear would go into this collision. And the relaxation time approximation tells us that whatever the mechanism of interaction is, the effect of these interactions is to take my system towards equilibrium exponentially. So instead of specifying the mechanism of interaction, what RTA does is it gives you the effect of those interactions. So you are absolutely right. It doesn't matter what the interaction is if we use RTA. So for the time being, we are assuming relaxation time approximation. Now, of course, if one has to have some realistic interactions, so basically, like if I want to have some spin orbit interactions, okay, so that has to be put in. So there has been some recent work which tries to develop this scattering, and the scattering. So for example, to do scattering, and for the scatterings to conserve angular momentum, this phenomena of side jumps are introduced. Okay, so these are so the mechanism of interaction has to be very carefully specified. So we bypass all that when we consider the relaxation time approximation for the collision term. So this is not answering the question, rather bypassing the question, I would say.
Sayantan, any you want to extend the question or? Okay, then Najmul has a question.
Yes.
Is this okay? Sayantan is.
Yes, Shanti.
Yeah. So then there is a follow-up question. So
yes.
You take the same relaxation time for spin degrees of freedom and all other degrees.
Yeah,
So
right.
what guarantees that
Yes,
that you
yes.
can take the same degree, same relaxation time, or can there be possibility of different relaxation time for
Right. So actually,
different of
that's a very good question. Actually, you are absolutely right. There. So I have. So actually, what if I interpret this question? So what actually it means is that there could be multiple relaxation time scales. Okay, for different processes. So why do I take them to be the same? One single relaxation time scale. So actually, you're right. There are in general. So this Clifford algebra decomposition, which I started with, the Wigner function, and its Clifford algebra decomposition. If I take the Wigner function, and then there are actually only two independent, a scalar so in the decomposition there are only two independent components, a scalar and a axial vector. Okay, so there are only these two independent uh, components. So in principle, I should consider two different relaxation times. Okay, so that should be the case. You are right. So here, this is more simplified relaxation time approximation. So I should have actually used a different relaxation time, and then the formulation would become a bit more involved. There would be some cross talking between the two relaxation processes. So instead of doing all that, so this is I would like to stress that this is the first approach to dissipative spin hydro. So we are trying to make baby steps. So we take the same relaxation time scale for all the processes.
Yeah, thanks. And also it's very nice work. So congrats.
Understand. Thank you.
Okay, so there are other questions, but because I have a related question, maybe I can ask.
Yes, yes.
Usually, you can find out what are the general form of the constitutive relation by constructing an entropy current, right? That is this classical Landau method. You construct
Right.
an entropy current and try to find out what are the possible constitutive relations that can contribute to dissipation. By requiring that the entropic current has positive definite divergence. So have you
Absolutely.
tried to look into that also, this way of doing things?
Yes. So we tried that. We have not been able to solve it. So it's a bit. It becomes. Yeah, it's a box of. It's a can of worms. It's too much to handle. I would say the algebra is too much to handle till now. So we are still on it, and we hope that we will be able to make some progress in that direction. That's an approach which one should do, because that's what usually leads to this local entropy divergence being positive definite. That's what leads to the constitutive relation, right? So if we can have such a thing going here, then we would not be bothered about going into the decomposition. Rather, we automatically would have the constitutive relation. So that is something which we are working on, but it's a bit tedious.
Even at linear order in omega, it is tedious.
Even at linear order in omega, yeah.
Okay, so then there are two people asking the same question, Najmul Haq and Sukanya Mitra. Is the spin in your story classical or quantum?
Oh, okay, that's okay. So let me go back. So this is actually so-called classical treatment of spin. So what do I mean by classical treatment of spin? So let's look at this ds, the integral measure over the spin that I have introduced. So actually, if I was working with quantum spin treatment, so I would, instead of integrating over s, I would be basically summing over the two spin states, right? So basically integral over ds, which I write to be 2, is actually the number of spin states that I should be summing over. Now the point is, there is an issue with relativistic kinetic theory. So I have to. So basically, the distribution function is, in this case, we have to assume to be a continuous quantity. It's not like a spin density matrix. So the point is that, yeah, we have made a classical treatment of spin in that sense. So it's a semi-classical treatment.
Okay, so Najmal, you want to extend the question, or Shukanna, or you want to extend the question too?
Hello, am I audible?
Yes, yes.
Yeah, Amaresh, can you go to your slide 8?
Sukarna, you're very loud. Can you just tone down the volume a little bit because it's really
Oh,
bursting here?
now it's okay?
Yes, thank you.
Okay, thank you.
Okay. Yeah, 8. Slide 8.
I'm sorry, maybe it's not slide 8, maybe it's some. Okay, the slide where, next please, where you have described that your spin is actually, this one. That is,
Yes.
you have defined the spin for vector S alpha in particle rest frame, right?
Right.
So that means, but particle rest frame means water rest frame. So this is not your fluid rest frame.
No, this is the particle rest frame where the momentum of the particle is just m000.
Okay. But then you are saying that your S alpha is orthogonal to U alpha, right?
No, no, no. S alpha is not orthogonal. It's orthogonal to P alpha, the particle momentum.
So S alpha do not have any relation to your hydrodynamic for velocity.
No, no, not at this
No,
level.
no, no.
No, no.
Okay. So it means at this level, from the definition of your distribution function, your S alpha from this definition is purely microscopic.
Yes, yes, absolutely.
Okay, okay. That is what I was going to ask, because in your particle distribution function, I can see there is one S mu nu with the coefficient of W mu nu. So in
Right.
this equation, your S mu nu is completely microscopic definition defined in
Absolutely.
particle rest frame. And that
Absolutely.
is why, as the Lagrange multiplier, you have introduced the vorticity tensor W mu nu.
And that
Like,
is the macroscopic quantity.
that is the macroscopic quantity. Like in case of momenta, you have introduced temperature. In
Right.
case of baryon quantum number, you introduced mu by t. Okay,
Right.
that is what I was going to ask. Thank you very
Okay.
much.
Okay, a related question also from Golam server. Is the spin here a localized, thermalized? Maybe Golam can ask yourself. Is better.
Yes.
Yes. Thank you for very nice talk. My question is regarding the same discussion this earlier asked by Nazmulda and Shugana. They were asking that you are defining this spin, treating this spin as classical.
Semi-classically. Okay.
Semi-classical.
Yeah.
But
Okay.
I think that this question is spin is arising from quantum effect, but particles are carrying that. So you are treating that as thermal averaged over some special cell. So that is like a field over a space.
Right.
So am I right? Is this your treatment?
Yes, yes. So basically, imagine. So imagine that so I have to make an average, thermal average over the microscopic degrees of freedom to obtain the macroscopic quantities. Okay.
Yeah.
So in order to, so now the two things that I am averaging over, the microscopic quantities that I am averaging over, is the momenta of the particle and the spin of the particle. So this is the idea of constructing the spin current as well. So
yeah, thank you. And then another question is that how much it is valid that your spin and angular momentum separation is separately conserved. I mean,
yes. Okay. So
this
that's
LS coupling.
So if I do yeah. So let me go to the slide again. So I said that if T mu energy momentum tensor is symmetric, then the orbital part of the angular momentum is automatically conserved. Okay, so d lambda L lambda mu nu is just antisymmetric part of T mu nu.
Sure.
But since T mu nu is symmetric, which is classically always true, so then this is conserved. Okay, now for the total angular momenta, J is the orbital part, the spin part, and some LS coupling. So see, we don't really know the form of LS coupling. So for the time being, what I said was, okay, let's, so if we don't have LS coupling and the orbital part is separately conserved, then total angular momentum conservation actually implies spin conservation. So this is, L is conserved. So for J to be conserved, I just need to conserve spin in absence of LS coupling, so any couplings. Okay.
Sure.
So this is, and then we work with constructing the spin tensor.
Sure, sure. So this LS coupling thing is playing the main crucial role here for your
Yeah.
adoption.
So
It is
one has
unknown,
to
so
somehow specify the LS coupling. So there is this. So what actually we found that at linear order in omega, yeah. So we found that hydro background equations are not affected. Okay.
yeah,
So that leads to, so if you are doing this linear treatment, okay, then even in S we will so that's the expectation that at linear order the LS coupling would not contribute. So at linear order we are valid in ignoring LS couplings, these coupling terms as well. Okay. But this is only when we have small polarization. In the limit of small polarization, we can actually ignore the coupling terms. That may still be true. Okay.
yeah.
However, yes.
Okay. Another, thank you. Another question regarding maybe related to this is that when you define your spin tensor in terms of momentum and the spin vector, there probably if you consider a position vector and 4 position vector, when that small s mu earlier
Yes.
side.
So here, yeah.
Yeah. So spin vector and momentum vector anti-symmetrized. So then my question is that
No.
if you take why you have left out the position for vector? I mean that. I mean, you can construct S mu in terms of you have 3 for, I mean, position for vector, momentum for vector, and your
No,
spin
but
for
this
vector.
is
But
intrinsic spin. It cannot depend on position.
okay. So this is spin, not angular momentum, total angular momentum.
No, not
Total
the
angular,
orbital angle.
total angular momentum. Okay. I see.
This is intrinsic spin. Yeah.
Yeah. Thank you.
Okay, so I have a related question. So in free streaming theory, in free field theory, the L plus S, L and S are separately conserved. So I think, so the LS couplings can only come from the collision kernel, right?
Right. So you are right. So you see, one is justified in asking whether when I have this dissipative framework, then should I ignore this LS coupling, right? So the claim is that actually, since even this dissipative framework, so there are 2 expansions in this theory. One is the gradient expansion, and the other is the small polarization expansion, right? So in the limit of small polarization, the claim is that this coupling term would also not contribute in the limit of small polarization. So, but however, so because the linear, so it's a technical thing that the linear integral over S vanishes. So it only appears at nonlinear omega squared and higher order, and the coupling would appear also at higher order squared omega. So that this is something which works pretty compactly in this linearized regime. However, if one has large polarizations, then it seems that then things will become a bit more complicated.
So Amaresh, another.
Yes.
Another question is that in your the S mu the consecutive relation for your spin tensor that you have obtained up to first order, there the theta term is there probably.
Yes.
Yeah. So this is some. You were saying that spin. Okay. So my question is like that this spin dissipation is somehow. Like
Right.
like this is like somewhat something like your bulb viscosity. So this expansion is this radial expansion is affecting your spin dissipation. How?
So it is more like if I invert in, so it's like a corollary. You see that actually the spin dissipation is affected by all the dissipation in the system. So
Yeah, yeah,
it
yeah.
has a dissipation due to total divergence. It has a dissipation due to shearing effect. Okay. It also has a divergence due to gradient of charge current. Okay.
Yeah, yeah, yes,
So,
sir.
so however, this derivative of omega polarization doesn't affect the other dissipative quantities. So the claim is that while dissipation in spin is affected by all other, the spin evolution doesn't affect the hydrodynamic background quantity. So by background hydrodynamics, I mean that so hydrodynamics evolved as if the polarization doesn't exist. Okay, and then
Yeah,
you have
yeah.
polarization evolution on top of that. Okay,
Probably this is due to
linear.
left out this linearity. I mean, the
Yes.
LS coupling is left out because LS coupling is
No.
the hydrodynamic field would enter in the equation through L. I mean, your position
Yeah,
and
but
spin.
even in the absence of LS coupling, if I go to higher order in omega, okay, then I will have all these interrelated dissipations. Okay.
Sure, sure. Sure. There was a PLB paper by they derived this first order consecutive and the relation using entropy current method. So they have their calculation actually they have not considered the conservation of angular momentum and spin separately.
Yes, yes.
So there you get term like theta times your spin field that is contributing to your hadronic field, dissipation of hadronic field. So
Yes.
then that's why I was a bit
Yes, yes.
surprised at this.
You are talking about this recent work by Charles Gale, so the McGill group, right?
Yeah.
Yeah. So that has been another recent art paper. I should have mentioned that in the list.
Thank you.
Okay, so I see no further question now. Okay, all right then. Thanks, Amaresh, for this nice talk again.
Thanks, Ayan.